Everyone who's coming out so early. This is the parallel Python data analysis tutorial. Quickly, while I'm talking, you can go to that repository at the top, download things and start installing. There's also a small script you need to run in order to just prepare some data locally on your machine. It'll take around 5 to 10 minutes, so it's nice to start early while we're sort of yabbering up here very briefly. It's also this link here at the bottom of the slides. So, my name is Matthew Rocklin. I work on a parallel programming library called Dask. I work with Continuum. This is Ben Reagan Kelly. He works on a Jupyter, also on a parallel programming library called IPython Parallel. This is Ben. He works for Continuum. He also works on lots of parallel deployment things. He gets things to work. We wanted to make a tutorial that was about parallel computing, but wasn't about any particular tool. I want to make sort of a more general tutorial. This is our first time presenting this material, so there might be some rough spots. Fortunately, we have some very nice volunteers that will be floating around about the room. So Jim, can you just raise your hand briefly so that guy can help you? Any of us can help you. Are you around for help? Chris here in the front can also help. And some other people wander around. There's lots of solutions if you can't get things installed. We're going to start the day with single machine parallelism. So your laptop has a lot of parallelism just in it. I'm going to start with that. And then the latter half of the day, we're going to use a cluster. So we have a website you go to, you'll click a button, and you'll have a cluster deployed for you. If you can't get things installed, we'll just switch you to the cluster sooner rather than later. Anything else we want to talk about?
No, that's good.
Okay. So again, go to that repository, start doing things. Min is going to take over for the first section, and all of us will jump in a bit afterwards. Great. Thank you all.
Okay, so just double checking before while I'm doing the talking bit at the very beginning, make sure that you've cloned everything. You've got the you have the notebooks, and you have installed the packages, and then you've started the prep.py, run the prep.py script, which will take a few minutes and generate the data for you. So the general structure of the information we're going to talk about today is 3 broad categories of parallel algorithms, ways to do parallel computing. The first one is called map. So this is the simple case. It's common. There's lots of different ways to do it, and there are many implementations of map, and it has kind of a balance of simplicity and flexibility. And then there's a submit model where you have kind of total control over the how the parallelism happens, where you just say, do a bunch of things, but you're doing them asynchronously, which lets some scheduler do them concurrently if the resources are available. And there's collections, which are kind of higher level APIs around parallel data sets that let you do, can be more restrictive in what they can do, but because they have information about the data you're working with, they can make smart choices and do especially efficient things. So the simple case of map is often in your code. You might have snippets that look like these. So maybe you've got a list and you're iterating through some inputs and producing outputs. There are a few common ways to spell this kind of operation in Python. So you might have a for loop where you're appending items to a list, or you might have a list comprehension where you're just saying, for every input, call a function on that input and save that in your outputs. And there's a built-in function in the Python language called map. And what map does, map is itself a function, and you give it a function and then a collection of inputs, and it gives you a collection of outputs that are the result of calling the function on every one of those inputs. So we have this figure of your computation represents a collection of independent inputs. You call the function on all those inputs, and you get a collection of independent outputs. And part of this is very common, and because it's so simple, it's implemented many times. So many libraries have an implementation of map. Essentially, anything that represents an API to computing resources probably has a map function or method that allows you to use those resources. So common implementations in Python include concurrent futures in the standard library in Python 3, Dask, IPython parallel, joblib, MR, multiprocessing, Spark, there's, and many more. So when you're using a particular implementation, it usually involves importing, from some framework. You import an API, and then you set up your connection to those resources, and then you have map as either a function or maybe a method on an object that represents your connection to those resources, and then you use that map function or method just like you would use the map method in the standard library in Python. And the nice thing about that is that you can write serial code, and if you can write your regular local running in one process program in Python, if you use map in that, then you can make that code parallel just by importing map from somewhere else. And then you say, okay, I've got my local one, it's just running in a single thread. I'm doing this to make sure everything's correct. And then, okay, now it's time to move into production. I want to move from 10 data points to 10 billion data points. I switch from the standard library map to a map that represents my broader compute resources, whether they're parallel on your laptop or on some distributed cluster. Oops. So now we're going to switch over to our notebooks in the repository. Hopefully your prep script has run.
So I think we have a quick announcement.
Yeah.
And also, again, please, if you're having trouble installing things, raise your hand, be very vocal. There's lots of solutions to things. But I think.
Yeah, just a quick announcement. There's an Nthought reception between 6 to 9 at the Nthought office at 500 Congress. There will be an announcement on Slack. There are links on our videos. Please be there if you can.
It's a good
We'd love
time
to have you.
Yeah, there'll be, it's great.
Yeah.
6 to 9?
6 to 9 today at the Nthought office, 500 Congress. You'll see an announcement on Slack or Twitter soon. Yeah, thank you.
All right, so the first thing we're going to do is we've got some data files that we built with our prep.py script. Just in case anybody didn't run it, we make sure that it gets run at the beginning of this notebook, which doesn't take any time if it's already run before. And what this gives us is a bunch of CSV, or some CSV and JSON data files of stock data. We have a small amount of real stock data, and then we've interpolated that with a whole bunch of fake stock data so that we have more points to work with, so that we actually have a fair amount of work to do without downloading a huge amount of data. So for our serial execution, we're going to load the data. So our file names, our inputs are just a list of file names. And so these are the first 4 file names. We've got these data JSON, and we've got kind of a collection of file names that contain stock data points. And each file actually contains a JSON record on each line. So they're not actually JSON files, they're files that contain lists of, on each line there's a JSON record. And so our task in this case is some data storage, kind of rearranging. So we've got a bunch of JSON files, and we're going to open those up, parse them, and then we're going to save them as HDF5. Yeah. Got people floating around. Just raise your hand and someone will come get you. And then we're using this %% snake fizz is a magic provided by the snake fizz extension, and we're going to use this to we have the snake fizz author in here, so that's nice. We're going to use this to kind of see what it's going to show us what is taking the time in our work, and profiling is important and can be challenging in parallel computing context. You want to know kind of where you're spending your time and where you want to try to make the most of your parallelism, or where you need to make things faster to save the most time. So you can run this, and this will take a little bit of time. It's going to go through each of our files, and then read it, parse it into a pandas data frame, and then save that data frame to an HDF5 file. And as you can see, this takes a little while, but this is the kind of computation that we described that fits well into map. That we've got a collection of inputs, that's our file names, and then our collection of outputs are new files that we want to make from those files, and that's independent. We don't care what the second file is when we're working on the first one. And so when the cell execution finishes, SnakeViz will open a new tab with a visualization of the execution. And what this is showing us is kind of where we're spending our time. So this is a hierarchical display of, so the cumulative time over here is, you can see it took 38 seconds to run the whole cell. And then as you go down, these are dropping down in the stack as you're kind of doing the steps of the computation. We're seeing where we're spending the time. So the first outer couple levels are just like run the whole thing. And then as we get down here, we can see, okay, so we're spending a significant amount of our time, 71% of our time, doing something in the JSON library. So if you look in the directory, it says, I'm in the JSON library in the standard library, and that's where I'm spending about 70% of our time. So in this read, parse, store, you can tell we're actually spending most of our time in the parse step. So if we've got somewhere that we want to make sure that things go faster, it's logical to look at this place first, which we're gonna see a little bit later on. And we can see that we spend some time converting the pandas data frame to the shape of data that HDF5 wants. Yeah. This diagram was run by running this cell. So SnakeViz produced this diagram. And I think we might need to, yeah.
Can I ask what SnakeViz is? I haven't heard of it before.
SnakeViz, do you want to take that?
Yeah.
Or just the author of SnakeViz, everybody?
So, I'm Matt Davis. I'm the author of SnakeViz and some other things. If I can go to the Min's already got it in his history. This is the site for SnakeViz. It's a Python library, so you can profile Python code with a module called cprofile. If you look that up, that's part of Python standard library that does timing of functions when you run Python code, and you can say like, hey, cprofile, I'm going to run this code. Please watch it and count how long everything takes in each function, and that can generate a file with all of the data in it. And then SnakeViz is a utility that you can use at the command line or via this magic in IPython that will generate this plot, which is by far the easiest way I've found to like view that profile data and find out like where time is actually being spent. You can also generate text output without SnakeViz, but it's much harder to parse and kind of see where everything is going on. Hope that helps.
Yeah, so we're using SnakeViz right now to see, it shows us where we're spending our time, which is generally called profiling. Profiling your code is a way of saying, what parts of my code are the things that are actually making it slow or making it take all this time. So you don't have to just guess, oh, that looks expensive, I'm going to need to do that. You run a profile and you can see, okay, I can tell that I'm spending all my time parsing JSON. Maybe there's a faster way to parse JSON. it lets you kind of figure out it lets you optimize your optimization work, right? So that you can focus on the parts that matter most.
Can I interject a moment?
Yeah.
Hi everyone. So who here is using Windows? Yeah. Okay. So, are there any Windows users who've gotten prep.py to work correctly? Yeah. Okay. One guy. Okay. Great. Okay. Yeah. Okay. So, prep.py works a little funny way. It downloads a tiny bit of stock data and then it interpolates that data to make it really annoying. That is like a small script we wrote up. It's not robust to Windows, it turns out. Fortunately, we have an alternative solution. So in the latter half of the tutorial, you'll all be given clusters to work with, and we're just going to have you, if you can't get prep.py to work right now, we're just going to hand you a cluster right now. You won't use the cluster, you'll just use like the main node. You can do that. Can I use your computer?
Yeah.
You can do that right now by going to scipy.2016.jupyter.org. So please don't everyone do this yet. Maybe just like let's ease in with Windows users. And then there's a very friendly button you can press. This button is courtesy of Ben Zaitlin and Min. And in about a minute, you should have a working cluster at your disposal with a notebook that just runs. The entire tutorial should work in there. So that's the failsafe. So, okay. If you are still a Windows user and you can't get that to work, please wave your hand wildly in about a minute. It should take about a minute to start. But, okay, thank you. Thank you.
It started. Okay, so now we've got, we've defined the work we want to do. We've kind of seen where we take our time. We can take the more natural, familiar for loop that we've written, and we want to say, okay, I've got a function that I'm calling on all my inputs to produce my outputs. I want to do this in parallel. So the standard library in Python has a module called concurrent futures, and this is a library for doing general asynchronous programming and basic local parallel programming. And with concurrent futures, you build an object that represents your computational resources. This is called an executor. And there are different versions, different implementations of executor that represent different kinds of resources. And the two basic versions of that are a process pool executor, which represents a collection of independent Python processes, and then a thread pool executor, which represents a collection of threads in a single process. And once you instantiate one of these executors, they have a map method, and you pass the function you want to call and the collection of inputs you want to call it on, and then you get an iterator on those results. So we want to just get all those results immediately, so we pass it to list to get a list of outputs. That's the result of calling our function on all our inputs. So here's just a simple example of we have a for loop that takes a while artificially, and we're just putting numbers in our outputs. Right, and this is going to take a few seconds, 8-ish seconds. So it's just iterating through our inputs, performing some action, and then storing some data in our outputs.
Excuse me,
Yep,
why do you have to sleep?
to make it slow.
Slow down.
Yeah. The sleep, yes, the sleep is there because if I were just doing this, if I took out the sleep, it wouldn't take any time, and then I wouldn't be able to measure the. I want to show that they're actually happening at the same time, and if they don't take any time, then it's hard to tell. So this is a simple case of I've got an artificial task that does something that takes a little while, and So in this case, it takes 8 seconds because I'm sleeping 8 times. The first step to parallelizing something with map, since map takes a function and arguments, the first step is that you need to make the action that you take on each input, you need to make it a function. In this case, it's a really simple operation, so why bother making it I wouldn't, if I'm in a simple for loop, I wouldn't bother making it a function because it's just 2 statements. So I don't need a function for that. But when you want to put it in map, then you need to make a function so that you have something, you have a handle on something to pass to map as what to do with each input. So now we have our slow increment function, which takes a number as input and very slowly increments it. And then, yeah.
What's the difference between this processable executor and the usual multiprocessing in Python?
It returns a slightly different kind of object. We'll talk a little bit about multiprocessing at the end, and then we'll also talk about futures in the next thing. But so they solve the same problem. They're largely very, very similar. But concurrent futures, the way it represents results that haven't results that don't exist yet, uses an API called futures that is kind of the modern current standard Python API for representing results in the future. And the multiprocessing.pool was kind of an earlier attempt at the same concept and used an API called async result that has a slightly different API. But the principles are absolutely the same.
And then will multiprocessing be deprecated in the future, or?
That's a good question. I would say probably not. But it's just a new API to the same thing. In fact, I don't actually know, but I would guess concurrent futures uses the multiprocessing library to implement process pool. That may not be true. Yeah, so there's no need to get rid of the multiprocessing library. It works, it's fine. It's just people came up with a new API that they like nicer for doing the same kind of thing, so they added that. So now when we run this work in parallel, this time it takes 2 seconds, right? Because I've got 4 CPUs on this laptop. The process pool, if you don't give it any arguments, it finds out how many CPUs you have on your system and creates that many processes, and then it hands that work, assigns that work to those processes as they become available. So I can ask for 2 instead of 4, and then this time it should take about 4 seconds instead of 2, because it's only doing 2 tasks at a time. Yeah. We have real-time feedback. Concurrent futures does use the multiprocessing library, so it's unlikely that it will go away. It's just new API for a nicer, more pleasant way of doing the same kind of work. So now we've got our first exercise for you guys. So we had our first work that actually did something real. It actually did took data, read it, parsed it, and saved it out. Now we want to do that in parallel. So we've got our task. It's a for loop. We have we iterate through our file names. Those are our inputs, and then we do some work on each of those. And then we kind of see how long that takes. And then what I want you guys to do is, with the process pool executor with the concurrent futures and map, can you do the same task and do it in parallel to see how much faster you can make it. So it takes about 30 seconds if we do it all in order. If you can see how much faster you can make it in the parallel case. Best you can hope for generally is the sequential number divided by the number of processors. That's what you get if your tasks are sleep. You'll usually get something less than that if your tasks are not sleep. we do it.
It's good to have you too. Snake is just not. Okay. So it's like opens up a server, it shows a thing, reports are open.
Yeah, okay. Yeah, it seemed like when I tried to run it,
Yeah. It's a great tool.
it seems great. Just, how am I reading this?
So
And then this is how long each piece was?
yeah, so this function this one. This is a list of JSP.
Okay, and then these are the sub pieces.
So this function has to open. Yeah. And
These get, okay.
if you want to, you can click on that.
Yep.
Okay. Thanks. Starting for writing process.
The typical, so what's the question is, what's the typical lifetime of a process pool executor? I would say it varies. There, so with the threads and processes, the processes take a noticeable amount of time to start. So it's common to kind of start them early on in your process. It's kind of, I know I'm going to do some work, allocate those resources, and then pass your executor handle around. Some things allocate the executor kind of, I'm going to do something, it's going to be parallel, allocate the processes, and then do it. With thread pool executor, that's very, very fast. With process pool executor, it's a bit slower. So usually you kind of want to do the allocation infrequently, because they don't tend to grow in resources, because typically you're passing around pure functions and things, so there's not generally a cost to keeping them around. So it's kind of keep them around as long as is feasible is usually the answer. There are some things that bring them up on demand, and you'll get a little bit of overhead. I mean, it's small. It's significantly less than a second generally. It's more expensive on Windows because it lacks fork. So opening a new process is quite quick on fork, or because of fork, and so it's Python establishes a connection in terms of how it takes the function to be passed. Python uses some communication mechanisms to do that, and that can take a tiny bit of time to set up. And on Windows, due to the absence of fork, it actually has to start up a new interpreter from scratch and take a new code path. So it takes substantially more time to instantiate a process pool executor on Windows.
When I tried to run the parallel from a couple of there was a executors.
Mm.
When we tried
That's not normal.
We have it on Linux and on Mac.
That's intriguing. Did you instantiate it twice like I did? Like, did you run it and then run it again?
We try to keep the one from a couple cells out.
Yeah.
Then we just use
Yeah.
one example and then try to make JSON example.
Like that? No, that's a pickle. So this is one reason why thread pools can be nice. That shouldn't take time. So apparently, there seems to be an issue if you leave a process pool executor open and idle for a long time, would be my guess. I don't know what's up with that. How we doing on the exercises? People got their map set up? You'll need a little more time. Need some software carpentry stickers. We got it. The function does not have to return anything. Technically, all Python functions do return something. It's if you don't return anything, it will return the singleton none. But yeah, in this case, our outputs we're saving to a file. So you can choose to, in this case, either return the new file name, or say I'm not actually doing anything with these files right now. Just don't return anything. Either one's fine. Yeah. Concurrent.futures will not provide any help in profiling. There are ways. I would not describe any of them as easy. Yep. Yeah. Yeah, how are people feeling on time on the exercise? Everybody?
I feel like a show of hands for like
Yeah.
5 minutes or 2 minutes.
Yeah, who wants 5 more minutes? 2 more minutes? Okay.
Who's not paying attention to you? Who's not paying attention to men right
Just
now?
raise your hand if you want to raise your hand. Just raise your hand if you heard what I said. Okay, give you 2 more minutes and then. No?
How is futures better than like multiprocessing pools?
So it mainly just defines, so the question is, how is futures better than multiprocessing pool? It defines a new interface that people like more. That is kind of a, yeah.
I read that it unifies the interface between threading and processing.
So one of the, it's not just that, so it provides a generic API for remote resources, or for parallel resources. So it has a thread pool executor and a process pool executor that behave exactly the same, that have the same API. There are some things that you can pass between threads that you can't pass between processes, but otherwise they're the same. And an advantage of that we'll come to a bit later is that this executor API, any library can implement that same API and be compatible with any other code that uses concurrent futures. So concurrent futures provides implementations of executors for local threads and processes on your laptop. But other libraries like Dask, like IPython Parallel, like JobLib provide that exact same API that potentially represent remote resources that are distributed across a cluster. And you don't need to change any code. You just change how you instantiate your executor. And that's not something that people do with the multiprocessing pool API. They could, technically, It's just people don't like it enough to do that. And people like the executor API enough to do that, it turns out. So it's more just multiprocessing network pool has been around a long time. People came up with newer, nicer ways to do the same thing. Okay, we've had our 2 minutes. We can look at check out our solution. So the first step is instantiate our executor and then change our work from a collection of statements in our for loop to a function. So given a file name, we open it, we parse it, we load it into a data frame, and then we write it out to an HDF5 file. And then to call it, we call a list on the map with our function and our file names. All right, and this should take less than the 30 seconds that the serial case took. Let's time it this time. All right, so this is going to take a little bit quicker. So now we've taken our work that we were doing that took a while, but since we were doing it on a bunch of different files, we can do those concurrently as long as we can express each operation on a file as a single function that takes that file name as an input. This time it took about half as long. That's not 4 times as fast, but that's okay. So now I've got the timing. We can try SnakeViz to say, okay, now where am I spending my time? How does the timing balance? Let's run it again with our profile to say, okay, now how do I make this go even faster? I've saved some time. How does it look now? And we will learn momentarily that we have a lot less information now. So now we run the program. It does its thing. Okay, we're actually spending just all our time waiting. So we're doing all our time waiting for things. And that's because SnakeViz and profilers in general profile all the calls, they monitor all the function calls and things in the current process. But we're actually doing all our work in a different process. So all we're doing in the local process is waiting for somebody else to do our work for us. And so when we profile our local process, then we don't actually have that information for what we were doing in our actual tasks that do the work. And so this brings us to kind of an important point in doing optimization, including parallel computing, is that a lot of the tasks involved in making things fast, figuring out what's going on, are a lot harder in parallel. And so you often separate the work of, all right, I want to make an individual task fast. I want to make that individual task fast, run it locally, do a single run locally, and I get all that profiling information. And then once you've kind of worked that out, then you move to the parallel case, where you typically sacrifice some information about what's going on, but now you're doing it in parallel and you're kind of scaling up to production. And so the next step is, why are we doing parallel computing? Generally, there's a couple of reasons. One is because you're doing something that takes a long time, and you have these compute resources. Everybody's got at least a couple cores on their laptop. And we're doing things in parallel because we have these computational resources and we want what we're doing to be faster. But an important point to consider is that parallelism isn't the only way to make things go faster. There are algorithms and implementations and all these things that there are other ways to make things go faster in serial, and they're just as important when you're doing parallel work as when you're doing serial work. So we learned from our initial profile of the first task that we're spending more than 70% of our time parsing JSON. So one of the ways to parse JSON faster is to Google parse JSON faster in Python. And what you'll find there is that there's a library called UJSON which is a fast implementation of JSON parsing in Python. And now we can run a profile again with just our original. It's the same as our original task, except we're using ujson.loads to parse our JSON instead of json.loads. We can see how long does this take this time. So when we did the serial case before, it took 30 seconds. How long does it take this time? Yeah, there we go. This time it took 13 seconds. So it's more than twice as fast just by changing our JSON implementation. So it's important to note that there are lots of optimizations you can do to consider even before you're working on parallelism. And then, as has come up a few times already, a little bit of background is that multiprocessing.pool is a similar, an older implementation, also in the standard library of Python. Going back further, and what this library does is it has this pool API for representing a collection of processes, and it also has this map interface that does the same thing. It's map, takes a function, takes sequences, and returns your list of results. So what have we learned so far? And the profiling is useful. We're going to profiling parallel is hard. We've got executors to represent resources that can run locally or in processes and threads, and that we can optimizations even when you're doing parallel computing. Optimizations of your individual task is still just as important as if you're not using parallelism at all. So now that we've learned about map, map is kind of the baseline. If you can represent your actual work as map, you're in pretty good shape. There's a million different tools that you can use to apply to perform your work on different resources, all with different performance characteristics and optimizations and things. But sometimes it's hard to represent the bulk of your work as taking a single function on your data and producing the results of that. It can be tricky to take. Maybe you've got some logic that says instead of calling my function, do something else. Right? In this case, I'm iterating through two collections, and I'm saying, based on a comparison of the item in those two collections, do one thing, maybe do something else. So this is similar to a map, but it's got a little. There's a little bit of behavior that you need to control. Like sometimes I want to do F, sometimes I want to do G. What submit does is it lets you take individual tasks. So map kind of automatically generated a task for each function call, and then let the executor assign that somewhere. What submit does is it lets you make one task at a time. So I say, produce a task for calling F on input 1. Produce a different task for calling G on input 2. And then it does the same submission and scheduling to run that code wherever and then give the results back. But you're only scheduling one task at a time. So it's kind of, you can think of it as like a manual map with where you get to choose what each action is. Like map, submit is a very generic call a function on an input type operation. So there are many implementations of it. Concurrent features, the executors have this API, Dask, IPython parallel, multiprocessing all have this kind of API. And generally, it looks somewhat similar to map, but instead of giving map a function and a collection of inputs, you give it a function and a single input. And then, so you call, you have your API, your executor API, and you call submit and the function, and then the arguments to be called with that function, and that'll send the work away, and you get back one of these futures. So a future is this API representing a result that is not yet complete. And then you call future.result to wait for the result and get the actual result back rather than the handle on the pending result. And so generally you iterate through your inputs, you submit your tasks, and then you've got a collection of futures instead of a collection of actual results. And then you have this extra step of, okay, I've got handles on all my results. Now I've done setting up my calculation, and then the last thing you do is, okay, now actually wait for my results to be computed, and then give me those back. So typically what a submit workflow looks like is you've got your outputs and your inputs, you iterate through your inputs, and then you build, you submit each task calling some function on that input, and then you put those futures in a collection, and then you have this extra step at the end of building the actual results out of the collection, your actual collection of results out of the collection of futures. And in this case, we're illustrating that it doesn't need to be a list, doesn't need to be an ordered collection, just needs to be any kind of container. In this case, we're using sets. Is there a typo? In the parallelism, yes. That's what you get for having code that's not. Yeah, these outputs should be futures. Good catch. So back to our notebooks. Now we've got a submit. And this time we're going to go through a workflow where representing it as a map, while technically possible, is a bit tricky and can be harder to follow. So we're going to build. So we've got our HDF5 files that we produced in our last notebook. We're going to read those into data frames, and then we're going to do some comparisons. So these are time series stock data, and what we're going to do is compute some correlations with pandas. So we start in the same similar way to the last notebook, where our inputs are a bunch of file names. In this case, the file names are HDF5 files, which are what we produced in the first notebook. And we've got a dictionary of series. So each series, we've got a dictionary keyed by file name, and it's just the close array. So series. Yep. I'm going to. All right, so it's just a pandas series of just numbers. This is the. I can just do. We can peek at our data. All right, so this is the data we're looking at. We've got one of these lines for every file name. So our inputs now are a dictionary of time series, where each from our HDF5 files. And what we're doing is computing correlation, pairwise correlation. So we've got, we want to iterate through all of our files, and then iterate through all of our, for every other file, we want to find the correlation of those two time series. So our results are a dictionary, and we're iterating through our left-hand side inputs, and we're iterating through our inputs again for our right-hand side. And then we exclude the case where you've got the same, where your left-hand side and right-hand side are the same, because they're the same thing. They're going to be perfectly correlated. And so excluding where the left and right-hand side are the same, we store in the results the correlation of A and B. And then our last step is we want to find the most correlated pair. So we use the Python max function, and we take the maximum. So results is now a dictionary where the keys are a pair of file names. So each key is file name, file A and file B, and then the values of this dictionary is the correlation between A and B, which is a number. And we are finding the maximum of those keys and values, sorting by the correlation value, sorting by the values. So then we have A, B, and correlation are the A and B that are most correlated, and then the actual correlation between them. So now we've got our best correlation is Yahoo and ABC. It's interesting. And they're highly correlated at 98-ish%. Okay. So we can look at those correlated series. So these are our two, the two series that we found that are most correlated, A and B, and we're plotting both of those and seeing kind of that they do actually behave have kind of similar structure. And so what did we do for to produce this work? We have our doubly nested loop. So this is a little bit more than our singly nested loop that we did for map. And we've got a bit of logic. So we don't want to do the task for everything. We want to do the task only when the sides don't match. You can represent this as a map, but it involves some kind of finagling and a bit of making sure that your iterations are a particular way and your function has some logic in terms of what it does. So instead of doing that, we're going to do this with submit. So each task you just submit as a discrete task. And then the last thing we do is a reduction on the data is to find the maximum. But since our sorting a small list is not very expensive, or finding the maximum in a small list is not very expensive, we're not going to bother parallelizing that because it's quick enough. So now I've got our slow add is back. So we had slow increment, which took one input and give us one output. Slow add takes two inputs, A and B, and it adds them together. And what we get is immediately, so this is a function that takes a while, but this cell ran very quickly because it returned us a future immediately. And then future.result gives us that the actual result of that computation. And so if you build a list of submits, so you schedule, I want to do this slow operation several times. What's going on there? Right. Yeah. So I'm actually performing that computation all in serial. That takes 10 seconds because I'm sleeping 10 times. But I can submit, and this will be very quick because that completes instantly. And then after I've submitted everything, I wait for those results. Right, and that took 3 seconds, which because 10 isn't evenly divisible by 4. Right, so we've got a mechanism with submit. You've got a bunch of tasks. You can schedule those tasks, and then you can wait and gather those results when you need them, and that lets you move on and do other things locally while you're waiting for your background work to complete. And so the nice thing about this is, yeah. Okay. Is there a question? No? Ghost question. Yeah.
In the last set of code, should this submit slow add be add I and I or 1 and 1? Or is there a reason there are ones and add and I's in the previous one?
It doesn't make too much. Yeah. So if we look at our results before, that's going to be a bunch of 2s.
Yeah.
And then if we do it right, then it should actually be, yeah.
Okay, thanks.
Since that was a synthetic one where we weren't super interested in the results, we didn't notice that the results weren't wrong.
You should always check that your parallel code matches the result.
Yes, always in the end have like serial result equals parallel result. Always do that, because in the beginning it will always be false. And then you only actually start using the parallel one once that's true. Okay, so we can parallelize our results. So here's an exercise for you to do. We've got a task where we've got some nested iteration and some logic to do different tasks, and then we call a function and store it in the results. And so the exercise for you guys is to parallelize that using submit. Let's see how it goes. Yep.
Is there a recommendation to submit together tasks that take roughly a similar amount of time?
So it depends how many. So the question is it recommended to submit tasks that take roughly a similar amount of time? The answer is it depends on how many tasks you have. If you have a very large number of tasks, it's not that important that they take a uniform amount of time, because the fast tasks will finish, and then more tasks will be assigned to the worker that did those fast tasks, and it kind of smooths, it kind of evens out. But if you've got a relatively small number of tasks, then you'll have kind of more consistent behavior if they're fairly even. The other thing is it's also nice to prioritize the ones that will take longer, so that you're if you start your tasks that take a long time, and then as they finish, it will start filling with shorter tasks. So it's you're stacking smaller pieces on. So if you think of it as kind of bars of the time doing work in each of your processes, then as you start with the big ones, and then you start stacking the smaller ones on top of those, and then it'll smooth out, because as soon as one finishes, it takes the next task. And if they go the other way, like if I did a map of sleep where the sleep got longer each time, I would be doing, and then if I did that forward, I'd be doing the small tasks, and then the last task would actually be the longest, and I would be spending. I would be more likely to spend a lot of my time at the end of the computation with only one worker. And so it can, if you know ahead of time how long things take, it can be useful to.
By order of submission, so it's just.
It depends. Executors can do ordered or unordered execution. It's up to the executor to assign to do that scheduling, and some executors let you exert some influence. The default simple behavior is usually to just run them in the order that they were given. In which case, it's on you to build the sequence in the optimal way.
So, with map, does it do something more clever, like sending off a chunk of your interval, or is map really just sending off single?
It depends on the map implementation. They can chunk. Some implementations can chunk, and others can't. So it depends on the implementation whether they chunk the inputs.
literally a for loop of
Okay.
Yeah, you can see from our I think it was maybe clearest in our slide, this slide. You can see this is map right here. We have our futures, iterate through the inputs, submit, calling that function with the input. That's what map is. So if you can implement submit, you have implemented map, basically. And then there are some libraries have a chunk size optimization that lets you say instead of building a bundle of this one operation to send somewhere and do, you do a collection and then you send that over, and then the actual single task that you're sending to someone is actually itself a map on that sub. Yes, joblib does that. It chunks and actually measures. It does some measurement to figure out what the chunk size should be.
Does the execution start right on the submit?
Yes. Well, again, that depends. In some implementations, it waits till you ask for the result, so that it only does computation of results that you actually need. And in some implementations, it starts immediately.
There are surprisingly few questions at the moment, because you all are geniuses. These buttons are quite important.
Yeah. So one of the things about these APIs is the contract of the executor API is very small. It doesn't guarantee anything about when or where those functions will be called. It just guarantees that the function will be called, and when you wait for the result, you'll get the result. It doesn't tell you anything about when it's going to start, where it's going to happen. It's just, and that's all up to the implementation. So things like concurrent futures start things immediately, and others do kind of lazy evaluation. So they only you can say, I'm probably going to execute this, but it only actually does it when you say I actually need the result of this computation, is when it says, all right, make sure you actually compute that. Yep. Task.cancel. There is future.cancel. Not all implementations allow that. Some don't have the ability to say, hey, please stop. But yeah, there is future.cancel. In some cases, you get a not implemented error. In others, it works.
So if you have a set of future or cancellation per future.
Yes. So the question is for future.cancel. Is it per future? Yeah. It's a method on the future object. So if you want to cancel the whole thing, well, one thing is to just destroy your executor and say, everybody stop, go away. And then the other is to cancel the individual futures. And there are some things that represent. We have a future that actually represents multiple results, and then that might have a cancel that cancels multiple operations. But it's always a method on a single future object. These slides are at. Yeah. The slides are at the README. Yeah. Oh yeah.
Yeah, maybe just show them themselves. If you're getting an int is not callable error, yeah.
Yeah. So here's my results is slow add. If I a common mistake when starting to use submit and map is to just take your function call and put it in submit. Sorry, Python parallel. Yeah, so we get this error that an int object is not callable. And so if you get that, that's because I actually ran slow add, and that gave me a number, and I just passed that number to submit. But with submit, what you actually need to pass is the function itself and the arguments. You don't pass the result of calling that function. So I actually, in this case, called slow add, and then took the result and then passed it to submit a number to go call the number, which doesn't make sense. That's why I got this error. So when you start with submit, you got the function that you called. You want to change that from a function call to making the function the first argument that you pass to submit. So instead of you don't call the function directly anymore. You pass the function itself and the arguments that you want to be called as the arguments to submit. Yeah. Yes.
So where in features does it wait for what you've submitted to execute? So say you submitted, I think someone else like you submitted like a fast job and a slow job.
Yep.
In this loop, where would it be saying, okay, now I'm going to sit back and wait for all the results to come in?
That's what result does. This result method returns the result, but it waits. It will only return it when it's actually here.
Okay.
So when I do this, this line happens very quickly, and then this line takes a second because slow add takes a second. Because a result will return that result when it's available.
So if you had, like, say, a process that took an hour,
Yeah.
You could keep on going after submit, doing everything.
Yeah, you could do a million submits.
But once you called result, then it would say, okay, I'm sitting back until
Yes.
this finishes.
And we can. I actually haven't looked at this in a bit, but let's see what happens. So result also takes a timeout. So you can say wait for this result up to this amount of time, but don't wait forever because maybe there was an error that meant that the result's never coming. And so this is how canceling works, and yeah, so this is the main thing, that it has some threading stuff for doing things in the background. So it says with a threading event object, I believe, which is a thing for waiting for other threads. It says wait, basically wait for my result to be ready is in the result method, and then once it's ready, that's when you actually return the result. This guy. So it says, wait for me to be ready. If I'm ready, return the actual result, is what the result method does.
Okay. Thank you.
So is results out of order when it comes back to you? Or is it in order preserved in preserved order?
So with submit, each future represents a single result. So the futures themselves don't have order because each future is just one result. So we put those, if we put those futures in a list that has the same order as the inputs, then if you iterate through the list of futures, they'll be the same order as the list of actual results. So each future is a wrapper around a specific result. Map, the contract of map is that it preserves the order. Again, some implementations allow ignoring that order if it's not actually interesting to you. So IPython parallel, for instance, you can say map ordered equals false, and then it will iterate through results as they arrive, regardless of the order that they were submitted. And you can build your own version of that. Like if you've got submit and you've got a bunch of futures, you can say, just while all the futures aren't done, look through the futures, wait for a little bit. Yeah. Oh, as completed, yeah. Yeah, in concurrent futures has an as completed for given a bunch of futures. With concurrent futures, there's an as completed that will yield the actual results, ignoring the order. How are you feeling about the exercise? Feel want a couple more minutes? Everybody good? Nobody's asking for a couple more minutes? Then I won't give you any. So our solution, it's just that it looks very, very similar to the serial case. It's just instead of outputs, we're paying to futures, and then we're waiting for the futures to get our results. Right, and this time took 20 seconds in serial, took 5 seconds in parallel because I've got four cores to do my sleeping. Okay, so now we've got kind of the basics of doing submit. The next exercise is to take our actual work. So the work we want to parallelize are these pairwise correlations. And so iterating through the file names. Then we want to compute the correlations and do that with submit. So produce your futures and produce your results. Yep. Sure. Yeah. People want a break? Coffee? People want coffee? Yeah, I see people want coffee. Okay. Let's have 10 minutes of coffee. We're working on our exercise of parallelizing the pairwise parallelizing our pairwise correlations. So we're building, going to build our dictionary of futures, and then we're going to wait for our results. So we need to build a function to submit that takes our A and B. Yeah.
I tried that and the timing was pretty much the same. We ate stuff, spending more time inside NumPy, spend more time just waiting for the thread.
It might be because we made the data smaller.
The question is, like, it's not always that much faster.
Yeah.
Should I?
Yes.
So on some computers, you may notice that this isn't actually a whole lot faster than using it sequentially. And there's some good reasons for that. There's actually a good example for exactly that. Parallelism is not always faster. You have more cores operating on the problem, but your cores aren't always your bottleneck. In this case, this doing correlations is actually pretty fast, and you're probably not CPU bound. You might be memory bound. And so you're different, even though you have more cores, those cores are all still sharing other resources that are not parallelizable, things like memory or disk or network. And so parallelism isn't always going to make things faster. This is one example. On different computers here, you'll get speedups, and on certain other ones, you won't, based on the hardware. So, yeah.
And another thing with this particular example is that you've got your A and your B, your input data. If you're using processes, you have to actually send that data to those processes. And that can be a not potentially overwhelming cost over the computation. And so that can be a threads versus processes example of threads can, when you're using threads for your parallel computation, you don't have to send data So starting the computation is much cheaper if your inputs are substantial data, like each input is a substantial amount of data. For threads, that's much quicker because it's just handing a pointer. But you're only going to be able to get concurrency if the body of your task releases the GIL, which is the global interpreter lock in Python that prevents certain Python operations from happening concurrently in multiple threads. So if you're doing NumPy operations and numerical array stuff, those do release the GIL, and you can do those in a multi-threaded context, and it's fine. But if you're doing something like our JSON parsing in the first notebook, that's bound by Python calls, and doing that in multiple threads will not be better because they're just going to be fighting over the GIL the whole time.
I noticed that in your code, you guys use the switch tier 4.
Yeah.
These rules found, or your rules found each processor T threads, and how do you guys kind of gauge that?
Generally, so most often you instantiate it with no arguments, and it'll just use all your cores. That's the norm. Sometimes you might want to deliberately use less than all of your CPUs because there's actually other things using your computer. So you want to say I've got 8 cores, but I only actually want to use 6 for this work because I want to leave 2 available to run my browser or something like that. You're actually doing other work. Most often you're just going to ask for all the CPUs on the machine, in which case passing no arguments, it'll figure that out and do it itself. You can also oversubscribe if you might be bound by external resources, like if part of your tasks are like waiting for something over the network, then it can make sense to actually have more processes than CPUs because you're not CPU bound, you're bound by something that you can actually have 16 processes waiting on a download, even though you've got only 4 CPUs or something. So it depends on that. And it's also your tasks themselves. Yeah, your tasks themselves can be multi-threaded. So if you've got, you might want 2 processes, and then each process uses 4 threads, and then you'll use all 8 CPUs. So you need to understand something about what your tasks actually do to determine how many resources to devote to each one. Okay, so looking at the solution for this guy, we've got our executor, and we iterate through our inputs, and we've got our futures with the call to submit, and our correlation just calls the method correlate on A with B, and then we get the result from our futures. Right, and then if we time that, you can see, right, we went from 2 seconds to about 1.5. So we only got a little bit faster because this is a small task, and we're actually spending a fair amount of time moving data around and stuff relative, or not moving data around, but we're not really purely limited by the CPU. And you can play around with threads and processes to see how that affects the interaction, how fast things go. Some things will be faster with processes, some things will be faster with threads, and it really depends on the nature of your tasks, how what kind of executor is actually going to be the best choice. So next thing, they're moving on from submit and map, which are just a function and some arguments, and you're calling that somewhere, are collections. And collections are these high-level APIs that represent kind of common data structures for large amounts of data in a particular shape. And there are different categories like distributed arrays for doing basic array operations, tables, data frames, tabular data for a bunch of two-dimensional tabular data, or things that are like lists. Like I've got just a big sequence, and then I want to do operations on those sequences. And there are libraries that provide APIs that kind of represent. You get an object that represents that data, and it has methods and operations that you can perform. And because it knows, because the object knows about the data and where it resides, it can do clever things about assigning that work and bunching it up into pieces and doing things in clever and efficient ways based on its knowledge about the data and where it is. So often they'll generally define a kind of a fixed set of operations that you can do on that data, such as map, which is common, filter. So say give me the items that match some condition. You can group elements. You can join collections with other collections, and generally these operations return. So you've got some object that represents your data. And when you call these methods, for many of them, you immediately get a new object that represents the result of that computation, and it doesn't necessarily actually perform that computation immediately. It only performs the computation once you ask for the actual result, or once you ask it to compute something that needs to know the values in order to decide what work needs to be done. And so things like this are implemented again by a number of libraries, a different collection of libraries. There's Dask and Spark and parallel databases and other libraries. Yeah. So now we can look at some examples of parallel data structures. We're going to look at notebook number 3. I'm going to go through the Spark example. Spark is a library that provides some of these data structures. I'm going to do Spark. We have 2 implementations of this task using that are almost identical. If Spark doesn't work for you, you can try the Dask example using Daskbag. They're almost perfectly identical and cover the same principles. Getting Spark set up might take a little bit of work. There's some covering of environment variables that you might need if instantiating your Spark context fails. But we're going to take the same work we just did in submit, and we're going to try to express that using these Spark data structures representing the distributed data. So we've got methods like map. So what this does is it's map on your data, but this is a map. This is instead of a function or a method on your compute resources on your executor. This is a method on your data representation. So your data has a method map that actually calls map on itself, and then gives you the result of that map. And then Cartesian, in Spark, this is called Cartesian. In Dask and Python, this is called product. They both refer to something called the Cartesian product, which is what you need when you have a nested for loop. You have for A in sequence, for B in another sequence, and you want to have all those pairs of A and B in a single sequence. That's called the Cartesian product of the 2 sequences. And so that's very common when you want to turn a nested for loop into a map. You generally want to compute the Cartesian product of those 2 input sequences. And then filter lets you take particular items. So we're going to create a PySpark context, just a local Spark context. And that will instantiate a kind of Spark API for a collection of local processes. And if that doesn't work for you, you can switch over to the 3B, the Daskbag implementation, which will cover the same kind of information. In this case, we use Spark context.parallelize. So we have a local sequence, and we tell Spark, here's my local sequence. Distribute this across your workers, and then give me a parallel API around that data. In Spark, this is called an RDD, which some redundant, resilient distributed data set. Yeah. So it's my distributed list. And so that is just an object that represents my data, but it no longer is my data locally. And I call rd.collect to actually say, all right, all you distributed guys who have pieces of my data, give me that back. I want the real thing locally again. And so this is like our future.result. It's all right. You've computed some stuff. Now give me the actual thing. your RDD has a map method, and when you call map, you get a new RDD. So you get a new, this is kind of like our features that are a representation of that result. You get a handle on the result that you can use immediately. It doesn't need to compute that actual call until you ask to collect the result. And you can filter operations. So this is saying give me all the even elements. So for everything where this function returns true, then give me only those elements. And then we can compute the Cartesian product, which is what you need for these nested for loops, where we take the sequence and then we take the Cartesian product with itself, and that gives us our 0, 0, 0, 1. This is our for I in range 5, for j in range 5. This gives us those iterations as pairs, because that's what you need for things like map with the nested for loop. Since each of these methods returns a new RDD, you can chain them. So in this case, I'm mapping a function. I'm taking the Cartesian, so I'm squaring it, and then I'm taking the Cartesian product of that with the original, and then I'm filtering those where the first item is even, and then I'm actually getting the result. So this is showing me I'm getting the Cartesian product of x squared and x, where for only the even values of the left-hand side.
How can you create a 3-tuple dot product does not give a 3-tuple?
Cartesian product is, what do you give it? 3. You can do 3. Yeah, you can give it.
You won't get a 3-tuple, you'll get a 2-tuple along with another.
Yeah, you need to append. You can add given two things, you can return. You can map, I guess, to flatten them. I'm sure there's a method that does exactly that. I don't remember how to spell it. And so now that we've got our expression for our nested for loop, so that we can use map to express a for loop, and we can use filter to maybe do different things based on some logic. Now we can do our parallelize. We load our data again. We've got our serialized version. And then what I want you to do is with Spark or Dask.bag, whichever one you've got working, express that with the methods on that distributed data structure. So we start by parallelizing the file names. So we take our local list of file names, and then we distribute that on our Spark cluster, which in this case is just local. And then using methods on that RDD or Dask bag. Can you do the same pairwise correlations using these Cartesian and map and filter operations? Yeah. Yes, there are things that Spark can do that Dask can't. Well, can't. Yeah, maybe can't is a strong word. So the question of how to choose between Dask and Spark is a tricky question to answer.
I'm really curious to hear your answer.
Yeah. So yeah, I have. I don't have a good answer for why to choose one over the other. There are, if you're already a big experienced Python person, as many of us in this conference are, you will have. There are advantages to Dask that it's all Python. It does all the Python things you expect it to do. There can be advantages to Spark if I would say the best thing to choose is the thing that the people around you already know, so that you have more people that you know that you can ask, how do I do this? That in a lot of cases it's a matter of taste, and there are certain technical things that will be better in one or the other on a case by case basis. But I think for the most part, it's actually going to be just a matter of taste.
So you wouldn't say that Dask is significantly faster for things as well?
There can be operations where Dask will be significantly faster. There can be operations where Spark will be faster. Yeah, there will definitely be performance cases where both win. It's not a like, you can't say that Spark is faster than Dask or Dask is faster than Spark. Neither of those is just true. So you can also say like you can do some research on, for my particular use case, Spark is really good at that, or for my particular use case, Dask is really good at that. But that's very very sensitive to kind of what exactly you're doing.
I would say a very big divider between the two is, do you want to be running in the Java runtime, or do you want to be running over Python? Because that will determine. So PySpark is Spark plus, PySpark is Java plus connections to Python, whereas Dask is native Python.
Yeah.
And there are going to be cases where if you're trying to run code outside of the Java ecosystem, for example, like scikit-learn, you're going to be paying a performance penalty every time you go back to it. But there are also going to be cases where your enterprise environment really wants to be running Java. So there's trade-offs on either side.
Yeah, so often you'll have for PySpark, often you'll be in a situation where your company or your group or something is already using Spark and Hadoop and everything. You can use Hadoop stuff with Dask as well. But if there already is an ecosystem of Spark and everything, the nice thing about PySpark is you can still use Python on all that infrastructure, and you don't have to do a concurrent deployment of Dask on all the same resources. And so if you've already, in a lot of cases, you've already got all your data loaded. Somebody else has already loaded all your data into Spark stuff, and so you can use PySpark to access that. But if you're starting from scratch, then often Dask will be a lighter weight choice to just get going.
So it sounds like you're saying if you're using most of the Python resources and you're starting from scratch.
If you are more of an expert in Python and like the data analysis workflow you have already built in serial is Python, then if you're like me and you like Python, then I would choose Dask in that context as a Python solution. I understand how it works better. I understand the errors it will produce significantly better. So I would choose Dask unless you find a specific reason not to, or a specific reason to use Spark for your particular data, if you're starting from scratch.
There will also be a talk on Thursday morning about Dask.
All right. I think I'll pull up the solution to this guy. So we've parallelized took our file names and built an RDD with our file names. And then we get a new RDD for all our series. So we map the file names and then use pandas to get the close price series. So this is a new RDD. And here's our nested for loop. So series.Cartesian series, this is our nested for loop of all our A's and all our B's. And then we filter those for when A and B aren't the same. So we've got our for A and B for all of them, and then the filter excludes the ones where A and B are the same. And then we map our function with a single argument, but that single argument is both A and B. So we take A is AB0 and B is AB1, and then max gives us the most correlated item. You can run that. Hopefully I didn't let it idle too long or something.
It'll take 14 seconds.
Okay. Right, and there's our result. So each of these operations just produced a new RDD, and it wasn't until we asked for max that it actually performed the computation and gave us the result. And just for comparison, a Dask bag implementation is the same. So from sequence, that's the equivalent to Spark parallelize. The map is the same. Cartesian product is spelled product instead of Cartesian. Filter's the same. Actually performing the correlation is the same. Max is the same. And then in Dask, we get a feature and we call compute on that to actually get the result. And so they're very much the same principle and work the same. And if you're familiar with one, you can switch back and forth to between those fairly efficiently. So another collection type. So that was the RDD and Dask bag are for these sequence collections. Another collection type is a data frame. So if you're familiar with pandas, this is a data type for tabular data. So we've got our original CSV data that we used, that we've been working with in its CSV form instead of the HDF5, and we can import Dask data frame as DD, and then we load not one CSV, but actually many CSVs. And now we've got a data frame that represents loading those CSV files, and it's got split up into 250 partitions. We can ask for the head. This gives us the head of our great big data frame, just like with pandas. In pandas, you have this describe method that gives you some summary information about your data frame, and that produces a new data frame. And then we call compute on that to actually wait for it. And this is a global operation. It's actually operating over all those CSV files and reading all those data and then computing some basic statistics about each column in our table. And we call compute to actually evaluate that. And just like our RDD, with a Dask data frame, we can chain these methods and attributes. So you can call group by the date. We can get the close column. We can compute the mean of it. And all of those operations are immediate. So we get a handle. When we call mean, we get just a handle on that represents that computation. And when we call compute, that's when we actually ask the cluster to perform that computation and bring back the result, which is itself a data frame. And then we call the plot method on that result to see what we get. Right, yeah.
What was the difference between needing that comparative compute for mean but not needing max? Like max implicitly evaluated numbers, but mean did not. Right?
Where was max? In the Spark example.
So in Spark reduction also did the computation. And in Dask.
Yeah.
Okay.
Yeah.
You say that.
Oh, for compute. Yeah, yeah. So the question was why is there a compute on the Dask example but not on the Spark example? And the answer is that reduction operations like max in Spark say that you want the actual result as time to evaluate it, and in Dask, the operations like that, reduction operations like that, are implicit.
Is there a way
yeah.
to be non-implicit in
or the way to be implicit in Spark, or the way to be not implicit in Dask?
I know there's a way to, well, I guess both.
You can call compute. Is there a way to instantly compute in Dask?
In Spark, I don't think there's a way to give you a lazy result.
Yeah.
Yeah, that's more.
Yep.
So I'll answer that too. In Spark, there's actions and transformations. So transformations are literally the actions do things. Dask doesn't really have that. It's everything is lazy unless computes.
Yeah, and Matt, do you want to skip the data frame exercise? For time?
Wait for 5 minutes and then switch on.
Okay. Yeah. So now that we've got our Dask data frame, if you're familiar with pandas, then you know you've got all these methods for kind of interrogating your data, for playing with it, for querying it, slicing it, finding, grouping things. And so there are various questions that you can ask of a table. What was the maximum value of a particular stock? When did that happen? When things like how to pull out time slices. And so you can use many of those operations, but not quite all in Dask data frames, Spark data frames. And so for now we can kind of play around, poke around our data frame that we've loaded, and do that for a couple minutes while I hand off to Matt.
Can I ask you to take your laptop?
Oh, I thought you were.
Sorry?
I thought you said you were going to use it.
Oh, okay, so what I suggest, so by the way, I'm Matthew Rocklin. I'll be leading for the second part of the tutorial. I work on a library called Dask, so full disclosure, when I talk about Dask, I'm probably totally biased. So that being said, I try hard. So I suggested we do the following. We talk a little bit about the data frame notebook, very briefly. Then we switch to the last notebook of the first section, which is sort of a try things on your own example with some scikit-learn data. And during that, let's take a 10-minute break. So people who want to sort of be fast in that can be fast. People who want to take a break can take a break. Then we'll come back and think about distributed computing. So maybe 10 more minutes of your time, then coffee, then back, and clusters. So that's sort of rough plan for the near future. Okay, so Min was talking about parallel data frames. Full disclosure, there's also a Dask data frame, a Spark data frame. It works quite well as well. Works quite nicely as well. Oh yeah, I don't have on my thing. Yeah, I'll just talk generically then. Your question was, how does Dask data frame compare to Pandas data frames? And so Dask data frames are actually just many Pandas data frames, just coordinated, many on the same machine or many on different clusters. So you'll still experience some pain from, say, moving data between different machines, but actually running data on a machine, it's the exact same as Pandas speed. So for some operations, you'll be faster because you get parallelism. For some operations, you'll be slower because you're moving data between different machines. It depends a lot. As with all parallel programming, performance is really a tricky question. I can definitely find examples that run much faster with Dask and examples that run much slower with Dask. So this Dask data frame notebook is intended to be actually fairly boring. If you know pandas, most of it should be sort of rudimentary to you. There are some examples in here that are intended to break in order to show you that not everything exists. Pandas is really complex, and there's no parallel data frame or parallel tabular system which will implement all of pandas for you. If you want parallel pandas all the time, you're never ever going to achieve that. Yeah?
With Arrow coming on, are you guys going to first on that with the Arrow data frames?
The question is about Arrow. So Arrow will help when we sort of deal with Parquet formats, like other formats that are more common in the Hadoop ecosystem. Arrow is not a data frame. Arrow is like a interchange format. But yeah, there's lots of things that Python, big data, tabular things are very exciting right now. There's lots of activity. But again, I don't want to talk about this too much. Dask data frames are neat. Again, we'll do a talk on Dask later. I actually want to skip over to the next section. It's okay, which is not strongly Dask related. So this is a machine learning example. Wait, let's first go back to slides for a moment. So Min just finished talking about 3 very different ways of parallelizing code. It could be Python code in different languages, could be distributed systems, local systems. We actually haven't made any choices that were specific to using threads, using processes, using clusters. All of the techniques you've learned were all algorithms, and they're all generally useful across a broad variety of contexts. We saw map, which is really, really common, and it's easy to implement. And so it was easy to find map that runs on a single machine in threads, single machine in processes, on a distributed machine, on your phone. There's lots of different kinds of maps. This is sort of the common case. We then saw for the less common case, where you have sort of more complexity in your algorithm, 2 very different ways of handling it. Submit, which was sort of very low level. You were then doing sort of all your own for loops. It was sort of this very small addition of parallelism into your code, where you were sort of in full control. We also saw collections, where you're given a broad set of operations, which do sort of common operations, and you sort of stitch those together. And so we sort of have a few choices. If we're just using map, we're sort of very happy. If you're doing something more complex, we have some choices to make. And those choices depend a lot on how you like programming and on the tools that you have around you. In the next example, what we wanted to do is we wanted to sort of give you the option of using any of the sort of tools you've learned before on a nice machine learning example. So there's not going to be a prescribed method to do this. We're talking about a problem, and then you're going to have a few minutes to sort of play with it. That'll also be the time of our break. So we have a lot of imports. Right, this is fine. Okay, so we're going to play with the handwritten digit data set. This is a classic machine learning data set. So this is supposed to be a 0, as written by a human on paper. And what we want to do is we want to make a function that classifies this image as a 0. So it turns images like this into numbers like 0 or 1 or 2. So let's go look at a different one. Look at the 5th image, which is a 5. Let's look at the 6th image. Also a 6. That's surprising. So this might be a 3. We don't know. So we're looking for a function that produces this. We're going to skip through most of the machine learning stuff. We're just going to give you functions that actually do this training. So these are functions. You can go look at them if you want to. For our cases, they're just functions we need to run a lot. So we're building models, and these models have parameters. So every machine learning model usually has a few parameters related to it. These are parameters that can control how it determines how it learns. And as with any problem, we're not confident about what those parameters should be. So we want to search over these variety of parameters in order to find good parameters that cause our model to learn well. Okay. Additionally, we want to perform cross-validation. So we have our data set. We want to split it into training and testing parts, maybe 80% training, 20% testing. But then to make sure we don't overfit on that data, we want to do many different splits. So maybe the first half for training, second half for testing, and then switch. So we want to do that same splitting a few different times. So we're going to have many different parameters to train on, and many different cross-validation splits. So we're going to start looking like a nested for loop, or like a Cartesian product. So we're seeing this sort of problem, and we're seeing how that maps onto how we think about parallel algorithms. And sequentially, what we need to do is just this nested for loop, where we're iterating over these cross-validation splits. So these are 2 arrays for training and testing. We're iterating over our parameters. So these are all the various parameters that can go into our model that are sort of chosen randomly. We're going to, this evaluate one function is going to fit a model. Then it's going to evaluate that same model on the testing data and return for us a score. How well did that parameter set do? So if I run that, it's running on 10 sets of parameters. It's going to take a little bit. There we go. Took around 12 seconds. And our last function from that file was just going to plot all of our parameters visually, so we can see how they're doing. So on the x-axis, we have this C parameter. On the y-axis, we have this gamma parameter. And the colors here, yellow is good. These are parameters that when our model fit, it scored very well. And dark blue is parameters where our model fit, it scored very poorly. So we're seeing a few nice parameter sets here, and some sort of poor ones over here. So we want to gain more intuition about what this sort of space looks like. So we want to have more parameters inside that image. But this is taking a while, so we want to accelerate this process. We're going to use parallelism. So your exercise is to parallelize this code using map, using submit, using Spark, using any of the tools that you've learned so far. And I recommend that people, as they finish, or other tools you know about. A lot of people in this room are very smart and have played with lots of parallel computing tools. And you could try something new as well. I recommend people put solutions actually into the Slack channel, just so we see what people end up doing. Okay. Once you have that parallel code running, you can increase this number 10 to get more parameters, or this number 2 to get more cross-validation splits. So let's do that for about 5 minutes, or for about 10 minutes. And during that time, also, if you want to check out, go get a coffee or something, let's come back at 25 past the hour. So when the big hand is at 5. Let's get started. How many people have finished? How many people are still working actively on things? Okay. How many people just are working on something else and are willing to raise their hand? Okay. About third, which is actually pretty good. Generally speaking, has the tutorial been going, should we be going faster? Thumbs up, please go faster. Should we be going slower? Please move slower, thumbs down. Or just about right? Keep him up for a moment, please. Okay. I'm seeing some thumbs sideways. I'm seeing a couple of thumbs down, I apologize. A couple of thumbs up, I also apologize. But we'll probably stay at about the same pace. Okay, so we have a few great solutions. Looks like there are, so Michael Johnson is using concurrent futures. We're also seeing someone else, Stefan Andrews, also using concurrent futures. Tomas is using Dask delayed, which is like concurrent futures, but slightly different. Jacobs is doing fanciness. So he's effectively done a map. So he's used the itertools product function to do the nested for loops, and then he's doing effectively a map inside of that single for loop. More concurrent futures. People like concurrent futures. Okay, great. I also like concurrent futures.
Can you use Dask bag? That's what I'm trying to use.
Yeah, question is, can you use Dask bag? Yeah, so there's two solutions here. Let's go look at the solutions we had. One is concurrent futures, which looks pretty much exactly like what other people did. The other one is using Spark. Use the same approach we did before with Cartesian to handle the doubly nested loop. Dask bag would have the same interface. So what's nice is that when we have some parallelism, so let's run this in parallel now, it runs faster, right? Let's time that. So I'm on the cluster right now. The cluster machines are actually pretty huge, so like 32 cores. So when I ran sequentially, I ran in 13 seconds, and I ran in parallel, I ran in about 1 second. Now that it's in parallel, and now that it's running a lot faster, I can up this number a bit. And so while previously I had an image that looked a little bit sparse, I'm now comfortable running on more parameters. It's going to take a little bit longer, but it's not going to take minutes, which is nice. Now we get a much more filled-in view of that landscape, that parameter landscape, and we can see that, it looks like this sort of range of parameters right here is all pretty good, and so that maybe gives us some intuition about our machine learning problem, about our data set. So this is a great example of using parallel computing on a relatively sort of a small data problem. This is not a big data problem; it's a small data problem, but using parallelism to gain more insight about our situation. This happens all the time. This is a super common use case of parallel computing. This example, by the way, comes from Olivier Grissel, who talked about it at PyData Berlin a few months ago. We're stealing his example. You can use it with Spark as well. It runs a little bit slower, but it's fine. Spark will run a little bit slower because it's not using threads. It's moving data around between different processes. It'll be a little bit jankier. I actually wanted to try, this may fail. I haven't actually tried this yet, but to give a little intuition, running this locally with, there we go. So this is on my laptop, so it'll be a bit slower. Run this with Dask, which implements a different concurrent futures interface. And it'll allow us to, oh no, got an error. What do we got? Yeah, we'll do that in the script a second. Never mind. Okay. There's software issues. Okay. Okay, so we have some choices about what to work with, and we can choose many different things. They're all equally valid. We chose to use concurrent futures, it looks like in this case. But it's nice to sort of see this nice example. Okay, so, yeah, question.
When I run the Spark example, my plotted results were a lot less dense, fewer points, and I guess that's not
Okay, so the concern is that the Spark example looks a little bit less dense. Can one of you guys look back there? Yeah, sorry. Okay, so we're now going to switch into a different, we're going to do the exact same exercise, but now on a cluster. So the next thing we need to do is going to be this exact same notebook, but we're going to use a cluster of machines. So if you haven't already, you should go to this website in your browser, and you should click the Start Cluster button. And that will give you an environment very much like the one you are using on your laptop. But instead, you will have a cluster of 8 2-core machines that are all running Spark and IPython parallel and are running Dask. That should take roughly a minute.
It's taking a really long time. Just refresh the page and try again. Okay. Yeah. I didn't know if that was okay.
Yeah, no, please bring those up, and also type in Slack if people have problems.
There's dot after
No, so it's SciPy 2016, no dot, .jupyter.org. It will also be in the Slack channel momentarily. Once you have that running, who currently has it running? Who has clicked the button and is still waiting? Who has clicked the button and something else bad has happened? Great. Okay. So when you get that running, go to notebook number 6 on distributed services. And this is just going to be a test to make sure that everything runs. So it should just connect to Spark, it should connect to IPython parallel, it should connect to Dask. We can verify that we have different machines by just running a function socket.getHostname on all of the different workers. So the question is, how many cores do you have? So you each have, there's one container that's running the notebook and everything, and then there's 8 different containers that are all running 2 cores each. So this should be a little bit more powerful than your laptop, but it's not huge.
us to get this cool dashboard to see how our clusters are doing?
Yeah, so while you guys are getting a cluster running, I was playing with what was happening before when this thing failed. I didn't have my workers running in the right directory with all the software in it. So the short answer is no.
Okay.
In this cluster, no. But I wanted to show briefly, just on my single machine, what's actually happening when you're running things in parallel. Again, Dask, or what library I work on, has some I'm biased here, has some nice mechanisms to visualize parallel computing. So we're actually seeing now my 4 cores on my laptop operate. Let's actually go ahead and start up another one just for fun. There we go. So this should give you some intuition about how what your machine is doing as it's running all of these little Simbit tasks. You've got a bunch of cores that are running little tasks over time. So over time, we're running these tasks, evaluate 1 on, looks like 8 cores here. So this is what your machine is doing. It's just sort of piping functions on your cores. When they finish, it gives it another one. There's unfortunately no way to give you this unless you're running Dask locally on your machine. But
What's the command that you execute to get that best word?
go to distributed.pydata.org, and there's setup instructions there. But that's just me giving you eye candy for some other time. We could give a separate tutorial on Dask, but it would be a long tutorial. We intentionally wanted to give just a general parallel computing thing instead. Okay. Okay, are people, who's ready right now? Who's set up? Who's still getting things set up? Great, okay, sorry friends. Okay, so your next exercise is going to be exactly the same as your last exercise. So we have this cross-validated parameter search. Notice I'm now running on the cluster, not on my local machine. So you should also now be running on the cluster, not on your local machine. And okay, so let's actually go to some slides for a moment. So distributed computing is complex. Parallel computing generally is complex. In parallel computing, lots of bad things can happen, and we run into lots of those bad things. Distributed computing is even worse. Okay. So on a single machine parallel computing, you still have a lot of shared hardware. You have the same file system, you have the same hard drive, you have the same software environment. No one else is simultaneously trying to use your computer. There's a lot of things that you can sort of take for granted. When you switch to a cluster, things become harder. For example, if you write a .py file with some code, that .py file is not necessarily replicated across your different machines. So we need to find some way of sharing software environments, content environments, software libraries. Maybe you have different NumPy libraries on different machines. Things get a lot weirder a lot quicker. Additionally, there's a question of how different processes communicate to each other. We've seen a little bit of this already. So on a single machine, we've seen a little bit of using threads versus processes. And so on a single machine, when I'm using threads, that means that I have many cores that are all sharing the same memory. That's more or less what it means. They're all living in the same Python process. They can all share data back and forth without any cost of transfer. There's some challenges here, though. So Python has this thing called the GIL, which means that no 2 Python threads can manipulate Python objects at the same time. So even though you have many threads active, one of them is active, then it goes to sleep, and another one is active. So a common solution to that is multiprocessing. We have many different Python processes, all with one thread, that all have a little bit of the data. This solves the GIL issue. They can all be running simultaneously, but they can no longer share data easily back and forth. Okay. And so this is why some of the problems, if you switch from threads or processes, it runs 10 times slower. The scikit-learn example runs a lot faster with a thread pool executor, because it's using threads, than it does using Spark, because Spark is using processes as to explicitly share data back and forth. And that's why you're getting that 10x slowdown. The process pool executor would be equally slow. So there's some interesting changes there, right? Do we want to have all of our workers in one shared space, or in different spaces to isolate them? So notably, NumPy and Pandas and a lot of C libraries do not have the GIL issue. A quick rule of thumb is if you're using NumPy and numeric code, use threads. If you're using pure Python code, lists and dictionaries and strings, use processes. So quick rule of thumb. Okay. Distributed computing is this same problem, but even worse.
Quick question, is Panda, is that only a recent release of Pandas? I thought that Pandas locked the guild.
Yeah, so the question is, does Pandas really release the GIL? And the answer is that as of 0.17, 0.18, a lot of things have been released. Actually, as a result of a lot of the sort of new parallel computing work that's happening now. So yeah, the Pandas people have released a lot of the group operations, join operations, some read CSV. It's been really nice. That's, again, recent. You need to be on relatively recent versions. Okay, distributed systems is the same idea. But now we have many different computers that all have to communicate data back and forth to each other. And we no longer have the luxury of a completely shared memory space. We need to communicate. It's forced. We have lots of extra problems because then we lose a lot of shared resources. Don't have the same disk, don't have the same IP address, don't have the same user accounts, don't have the same authentication. So most distributed systems that we use today, things like Spark or Dask distributed or Python parallel or a lot of SQL databases, have one central process running on one computer. This often goes by the name of scheduler or master or controller. And that process coordinates many other workers that are on different physical machines. So for example, my computer might run a scheduler, and all of your laptops might run some worker. And there's communication going back and forth as one machine is coordinating all the others. It's not the only way to do it, but it seems to be the common way to do it among a lot of the sort of data processing systems. This differs from systems like NPI or other HPC systems, but the sort of central control is common. We then, as users, connect up to that scheduler, and we ask it to do things for us. And that scheduler coordinates all the workers. So regardless of today, if you're using Spark, or if you're using Dask, or if you're using Python parallel, or other things, this is sort of the mental model you should have in your mind about how these things work. When you give an address to something, like you'll be typing in Spark : scheduler 9000, that's talking to this machine. You're always talking to that central machine. Okay. You can think about data transfer between things. I'm going to sort of skip this just for time reasons. Ben, did you want to talk about the cluster at all? Yeah. Okay. So Ben's going to talk about the thing that you're all running briefly. You don't have to understand any of this. Ben is like the IT guy who's setting up your cluster. We wanted to give a little bit of flavor on how that actually works. Again, just so you have an appreciation of how you all have clusters that are all magically spun up and don't interfere with each other and have reasonable software environments on them. While that's going, the exercise that we have is, again, the exact same exercise you just did. So we have the same data set, we have the same functions, we have the same sequential solution, and what you're going to do now is you're going to take both the solutions that we've given to you from before, after this runs for 13 seconds, and you're going to parallelize them by using a concurrent futures implementation that's distributed, or by using Spark in a distributed way. So in the first section, we learned concurrent futures, submit and map. We also learned Spark and Dask bag and whatever. And all of that knowledge carries over into the cluster setting. So it's the same thing. We're just going to swap out a thread pool executor for a distributed executor. We're going to swap out a Spark local instance for a Spark cluster instance. So you should only need to change these two lines or change these two lines. You can get hints on how to do that by looking at the distributed services notebook, which tells you how to produce some of these things. So for example, Spark, you're going to give it this address. Or Dask, you can produce a compliant executor in this way. So, meanwhile, Ben. So Ben is going to talk about the magic he did to make that button work.
Hey, so it wasn't just me. It was Min and Nai and this other gentleman that works at Continuum named Daniel. But before we get to that, I want to just generally talk about, so how many people here work in academia and work against large machines? SunGrid Engine, okay. And what about like industry, corporate people that also work against? Okay, so hopefully in this section, we can have a little bit of a conversation that when you go back to those people, they can try and satisfy some of your demands. Because most of the time they'll say no. Right? So if you say, I want to run Anaconda, they'll say, no, you're running CentOS, you can have Python 2.6. That's the stable setup. Does that sound familiar? Okay. So hopefully we can try and bridge that gap a little bit. So generally the way that when we think about building distributed machines, we want to think about these four kinds of, four bullet points. How to deploy these different kinds of engines, whether we need to support multi-tenancy so we don't occupy all the resources there, how we do a little bit of resource management, so maybe people are using Slurm and they have a bunch of queues, or they're using things like Yarn or Mesos and they're building out small containers. And then how do we control the environment? So that's how do I make sure that all the Python libraries that work on my little laptop also work on my distributed environment as well. That's usually where things get a little sticky, because you can't really control, like generally all of us here should be fairly ignorant. We shouldn't have to care how things are set up. You should just be able to click the button, or you should just be able to log on to the head node and run srun or run Spark. It's not your job to care about those things, but it does become a problem when your environment doesn't match what you're actually trying to get done. Okay, so there's a couple ways of solving the environment problem. One is you just preload all the packages you'd ever want onto every single machine on the cluster. There's lots of ways of doing that. You can use the engine itself to actually bootstrap it. IT can be generous enough and just deploy everything onto every node. You can use NFS. There's lots of ways of chopping that up. You can also take the environment that you have, so maybe some of you are using Conda, you can zip all those things up. If you're using virtualenv, you can zip that up and push that along off with your job. And there's lots of ways of having Spark do that, or having Dask do that. A lot of other kinds of clustering technologies are providing that kind of mechanism to say, oh, I also want to bring along some friends to my other job. You can ship a spec of the environment, so list all the kinds of things that you'd want to install as part of your job. Go out and fetch those things and install them as a preamble to actually executing what you want to do. And then the last thing is using Docker. And there's a big star there because it solves a lot of the environment problems. I can just, or sorry, maybe I should back up. How many of you are familiar with Docker? Okay, so maybe like a half or so. So Docker is a technology which lets me pretty quickly bake a virtual image. Sort of, you can think of it. It's not exactly that, but I can take this image and I can run it on lots of machines. This is actually what's happening over on our cluster setup. And it solves a lot of these environment problems because I can just say, this VM should have this exact environment. I install all those things, and then I wrap it up in a way that lets me say, go run it on this machine, and go run like 30 of them. Yeah, so it's very useful in that sense, but it doesn't solve all these problems. Perhaps a lot of your organizations don't even use Docker, so it's sort of a non-starter. But generally, we look to these things, these containers and other resource managers, to let all of us users, all data scientists and quants and analysts, to control our own environment. So if you have something very static, you can't do anything. So SunGrid Engine doesn't work, or Slurm or Torque. They don't work unless you can NFS mount your home and change your environment locally. We give up a little bit of power to other resource managers and let them build out environments for us, essentially. So you should look for those kinds of technologies and go back and talk to IT about how do we leverage those kinds of things moving forward. So I wanted to very briefly describe how we actually built the setup. So we're using a piece of technology from Google called Kubernetes. Kubernetes makes it very easy for me to take lots of images, deploy them on lots of machines, and sort of namespace those images. So out somewhere in Google's cloud, we have, I think, 34 machines. Each machine has 32 gigabytes of memory, each machine has 208 gigabytes of memory and 32 cores. So we roughly have 1,000 plus cores and 6 terabytes of memory for all of you. So when you click that button, you get 8 workers and a node, 8 workers and a notebook, and it just happens somewhere on one of those machines. You don't really have to care where. The Kubernetes tries to bring things close together, but generally you don't care about it. So it sort of looks like this. This is maybe a poor attempt. So you click a button, it hits a web app that's running inside of a Docker container. It's proxying against, these are all the actual things that you're hitting against, and behind, oh, sorry, I can't, well, what? Oh, it's okay. So each one of those where it says Jupyter Dash, we sort of changed things a little bit, is what you're actually talking to. And blown up, what that is a namespace set of n workers and 1 notebook plus scheduler. So we can actually very easily say, instead of everybody here gets 8 workers, we could say everybody gets 100 workers, or everybody gets 1 worker. It's actually very, very convenient to do these kinds of things. And a lot of companies actually or not companies, but also academic institutions are actually trying to leverage these kinds of technologies that make things a little bit easier to scale. So throughout this tutorial, or right now, I could take a break and go add 100 more machines and make this even bigger if we wanted to. If we wanted to scale this out for, if all of us here decided that we want to form a company and now we need to run, 10,000 jobs every second, we could go and do that. And it's not, Kubernetes isn't tied to Google, it's just produced by them, it's completely open source. There's other things that do the same sort of setup. Yeah?
Would Kubernetes be complementary or alternative to things like Yarn and Mesos?
It's sort of alternative to Yarn. It's similar to Mesos in these things. They sort of, Mesos also can, Yarn can also deploy containers. Mesos almost exclusively deploys containers. But they're just solving very similar problems of, I have lots of compute, how do I make an isolated contained environment?
So it's a choice between one of those.
Yeah, there's sort of. There's reasons, people actually do crazy things where you can run Yarn inside of Kubernetes or run Kubernetes inside of Yarn, although those are a little bit weird, but.
That's sort of a special case.
Yeah. Yeah. Are there any other questions? Okay, great.
Now would also be a great time to thank Google for the compute hours that you're currently using. So they were very generous in providing a lot of resources for us to run right now. So you're all running on Google hardware, they're providing that hardware for free for us. So thank you, Google. Okay. So again, so the nice thing about Kubernetes is that it allows you, the user, to deploy, or the nice thing about the approach that Ben has taken is that it allows us to wrap up our own software environments and deploy them without IT having to really care. Google is not tracking what we're running, and they don't care that we're running our own thing. It's very nice to isolate those two concerns. Okay. So again, we have these two solutions, one for concurrent futures, one for Spark. And the nice thing about the APIs that we've shown, that we've learned, is that they are general. They're not restricted to a single machine. So everything you've learned in the last section, in the last couple hours, is now applicable to a distributed computer. So I can run this locally on a single machine, or I can make, let me just actually go and copy this. Or I can connect to a distributed scheduler. Let's go look what that looks like. The distributed scheduler is connected to 16 different processes across different machines. And I'm just commenting out this concurrent futures code. And let's actually, and now I can run that on a cluster instead of locally. Once I'm running on the cluster, I can easily sort of amp up the amount of work that I'm willing to do. And we can start doing a lot of that work. We can start scaling out to different machines. So this is happening a lot faster than it would have happened on a single machine. Oh, actually, on this cluster, this machine that I'm working on has 32 cores. So, but there we go. So we can now scale out. And we're using our same exact interface, as our future submit interface, to do that work for us. Let's do results equals f.result, or f in futures. This is taking slightly longer. So it is blocking on that result call. That's taking 1-2 seconds. That's because we're actually moving data from the cluster back to our local node. So something that was previously very cheap, blocking on this feature, it's actually causing data movement. So it's now more expensive.
So the progress bar earlier, was that the execution happening?
Yeah.
And this is just gathering the results?
Correct. Yeah. So this progress bar is watching all that execution happening on the cluster. Dask distributed is a little bit different. It's not going to bring back data locally. And this is both waiting until they're finished and then also communicating that result back to the local machine. So the API is the same as what you had in concurrent futures, but the performance guarantees are different. And it'll be different in IPython parallel. IPython parallel, I think, actually brings data back immediately. And so in IPython parallel, the result will be very fast and combination will be a little bit slower. So again, all of these libraries that implement concurrent futures, they all give you the same contract, sort of, but their performance differences will differ. And now we can, again, look at our result and we see this nice visually different result. This is qualitatively different than what we could do on a single machine. Okay. Again, with Spark is actually a little bit easier. We're going to replace this text local 4 with this text, which points to that scheduler. So if you recall, so again, we're pointing to that address of that central node that's running that Spark scheduler or that Dask scheduler. Okay. So if we just change that address, now Spark will, instead of doing the computation on the local machine, it'll send it out. And Spark also has great tools to show you progress bars. They're not as accessible inside the notebook immediately, but they still have them. So again, the things you've learned in the previous section are still valid today. Yeah, so the error that someone's getting is I can't run multiple Spark contexts at once. So you can only ever call Spark context once in a notebook. You can't call it twice. So if you run the same cell twice, you shouldn't do that. So I should probably have done something like this, maybe, so that I just create the Spark context at one time, and then I can rerun that cell many times.
And if you have done that, you can use sc.close on the old one, and then you'll be able to create it.
You can also just restart the notebook if you need to. Okay, so we've seen now in some simple cases, we can just switch out old executor for new executor, old Spark context for new Spark context. The example we just saw was actually fairly simple, and there was very little data movement. So the data moving around is actually fairly small arrays, and so it doesn't matter that much if we're a little bit sloppy. If you want to make this faster, there's other fancier things you would do. Okay. So we played with Dask data frames a little bit in the previous section. In this section, we're going to play again with Dask data frames, but now on a cluster. On a real data set. So we have the New York City taxicab data set. It is composed of 12 CSV files living on S3. Each of the CSV files is fairly large. It's around 2 gigabytes. In RAM, this blows up to something like 60 gigabytes total. So this is larger than you could comfortably fit on your laptop. Many Python users like using a library like pandas to look at this data. So if we just look at the data set, this is showing every cab ride in the city of New York for the year of 2015. And you can see, when the cab was picked up, when the passenger was dropped off, how many passengers were in the car, how long the trip was, and various things about the fare, the total amount of the fare, how much was tax, etc. Here I use pandas to look at a little bit of that CSV file, just the first 5 rows. And this would fail if I didn't have this little n rows equals 5 keyword argument. And that's what's stopping me from loading in the whole data and crashing my machine. Okay. So we want to have the same experience. These large data frame objects like Spark data frame or Dask data frame will give you that experience. It'll give you a pandas-like experience on large data sets. So we're going to connect to our cluster. And we're going to use the Dask data frame read CSV function, which, can I just show of hands who's very familiar with pandas? Who's not at all familiar with pandas? Okay. Not all familiar with pandas people, I apologize. Some of this should look somewhat intuitive, but you will probably be a little bit lost. Pandas people will sort of appreciate that read CSV looks a lot like pandas read CSV. What this is doing is actually loading a lot of pandas data frames on different nodes in our cluster. By default, this is loading just one CSV file, just for the month of January. And it's cutting up the CSV file into 32 different pieces. If you want, you can replace this 01 with a star to get all of the data. But you may want to wait until you have a bit more experience playing with the single node data, single file. Okay. And then this object, this df object, looks just like our pandas experience. Except that, as we saw before, if we do something like, say, compute the passenger count, the sum of the passenger count column, it's going to be lazy until we eventually call compute. And when we call compute, that's actually calling sum, passenger sum on all the different machines. It's coordinating all that data together into one machine, to one place, computing the sum of that, and giving that the result back. So, like in the previous case, we're going to play a little bit with Dask data frame, just to get a feel for how distributed data frames look and feel like. If you're familiar with pandas, a lot of this will be familiar. There'll be some things that are not familiar to you, some things that are a little bit weird and new. So, for example, we now need to manage that our data frames are living across the cluster. If I want to make some computation and compute the result, I may not want that result to come locally. I may want that result to live and maintain itself on the distributed cluster. And so there's new operations on the executor, like persist, which will keep data outside, or scatter, which will bring data from your local machine and move it out to the network. So I'm going to give you an example here. There's some exercises. Hopefully you can follow these patterns to achieve some of the exercises. So what I want to do is I want to compute all of the rides in which the fare was positive. So oddly, there are some rides in New York City that are free. And we're going to compute just a few columns out of that. So this is a Dask data frame, and this is lazy. So it hasn't actually caused any computation to happen yet. To trigger computation, we're going to use this persist method on the executor. And persist is going to say, okay, I've made for you a recipe of what I want computed. Please go make sure this happens on my cluster, and give me back a new Dask data frame that is pointing to those results that are now living on my cluster.
So why is it persist and not compute?
So the question is, why is it persist and not compute? So compute will compute a result and then bring it locally to my local machine. So for example, up here, when I called, there we go, compute, this gave me a number back. It brought back the number, 2 million or so. I brought it 21 million. I brought it to my local machine. I don't want to compute this result because that would be too much RAM for my local machine. I want to start it working, but I don't want to gather it back. Okay. That's a great question. So, generally speaking, you want to call persist on large results and compute on small ones.
Is there some way to use persist along with distributed storage?
Questions, can you use persist along with distributed storage? You would use something like write CSV to HDFS or something. There's other ways to do that, but yeah. Okay. The work is being done in persist. Persist is asynchronous, so it's returning something like concurrent futures, turning a lazy result to you, and progress is tracking that result. This is actually fairly fast. It occurred in 0.2 seconds, and you can look at the result. And now on top of this result, we can do things like compute where the tip amount was 0, so all the rides in which there was no tip. How many stingy New Yorkers are there out there? and compute the result. Or say, count the total number of fares, and we can do some, some comparison there. Okay. So there are a few exercises that get sort of increasingly complex. First, we're going to use just the .compute method. So compute a couple of small things, call compute, and get a result locally. This is blocking, so it's not asynchronous. You can't use progress, but you'll be using a cluster. That's nice. Then we're going to use set index to change the datetime column to be the index. So pandas users will know that pandas is very nice at time series analysis. So if you set to a datetime index, you can start doing lots of things, like give me all of the rides that happened in January. That'll happen very quickly. And then we'll do this debugging thing towards the end. Okay, so let's spend a few minutes on that. Please ask questions while you're doing it. Yeah.
So when you call fares, it's actually not, it's retrieving it from the cluster storage and RAM, whatever, and then just bringing back the results to you, so like fares.head, something like that.
Yeah, so fares itself is a Dask data frame. So that's actually not all the data. You're not bringing the data back. So just like with Spark, you have this sort of proxy object locally, which is a sort of a coordination object that refers to a lot of data elsewhere. When you call something like fares.head, that's going to go to the first, it's going to find the pandas data frame on your cluster that corresponds to the start of your data set, and it's going to compute the head of that data frame. It's going to bring that back locally, and then display it on your screen.
So obviously, if you were using a cluster, that would be all, it would probably crash your computer if you're trying to just load everything.
We are using a cluster here, and head is very fast. Yeah. But if we want to say, so we would not want to do something like, fares.compute. This would bring all the data locally. In Spark, this would be something like fares.collect. We would not want to collect our entire data set. Because then again, you're moving gigabytes, maybe terabytes of data across wires, bring it to one machine and it can't hold it. Yeah. This should be tricky for you, by the way. So you should be raising your hands and asking for help. I would be amazed if this made sense to everyone. One of the problems with this kind of tutorial is that we have to expose you to lots of different systems without telling you very much about how any of them work. And so we've tried to isolate you to various small parts of the API, but you're likely to run into other parts. So please be vocal in requesting help. Yeah, so there's a question on what's the difference between parallel computing and distributed computing. That's how I'm going to interpret your question, and I think the answer will be present in there. So parallel computing is when you're doing many things in parallel. So I'm running these two functions at the same time. That could be on a single machine, that could be on different machines. So parallel computing is a very general term. There's often two different, you can split parallel computing in two different ways. One is shared memory, or shared resources, where I'm sharing the same memory space, or I'm sharing the same hard drive. It's usually on the same machine. Or distributed memory, where I'm on probably different machines that have isolated resources that are not shared between the two systems. So, but they're both parallel computing. Parallel is a very general word. Single machine or distributed might be a speciation of those two. Okay. So I'm going to do yeah. Yeah, that's my fault. Let me get to that in a moment. There is something wrong with the results if you look at it. But okay. So I'm going to do a couple of small things just to sort of kick people forward a little bit. So in the first, so in the first section, so if you're writing pandas code, oops, we could compute these results by saying df.passengerCount.mean. And this is sort of standard pandas code that would take out the passenger count column and compute the mean of that column. Normally, with a system like Spark or with Dask, that'll always be lazy. Well, not with me. But, as we're going to add compute onto the end of that, that's actually going to tell the cluster, okay, I want this thing now. Go off, compute the result, bring it back to me, please. The second thing we're asked to do is a group by operation, which is a bit more complex. We're grouping by the passenger count column, taking out the trip distance column, and computing the mean per count. And so we find that, sorry, my notebook's a little weird. So we find that single passenger rides tend to be a lot longer than multi-passenger rides. The next set of exercises is a little bit complex because you're asked to set index. This is changing the index from sort of a nonsense index. This is the leftmost column to something that is based on the pickup date time. And this is actually going to take a little while. It's actually we're taking all the different data sets, all these different parts of the computer, and one machine might have some of January, another machine might have some of January, and we just sort of move them all around to different machines. So there's actually a lot of work that needs to happen to make this work well. Once it does work, notice on the left here we have all of our data set very nicely ordered by time, and so time operations are now very fast. But there's a big difference. Sorry, my mouse is doing something weird. There's a big difference here between pandas and Dask data frame in that setting the index is now really expensive because our data is on different machines and the data has to be moved around a lot. So communication has sort of changed our landscape of what we think of as being cheap or expensive. Once you have this cell, everything in this section should be easier. Yeah. So the question is, I don't have these things when I run this exact code. I suspect that you didn't include this. And I suspect that you didn't include this.
That might be the first load only loaded one file.
I'm also using just one file here. Yeah. So it's worth pointing out all these operations, again, in Spark or Dask, will always be pure. They'll never change the object itself. You'll always need to assign to a new object. Otherwise, yeah. So we're always making new things. We're never changing things in place. Lots of things that you can't do. Like you can't say df, dot loc of 5 equals 100. You can't just sort of like insert data into our object. We can only do the big common operations. Lots of things we can't do. So a lot of people want to do things like for I in range 100. You might have pandas code that does something like this, that walks through a data frame and inserts data. These operations are no longer possible. Lots of things that have sort of gone away. Okay. And if you have this section, this cell, this exercise should be easier.
If you had or really wanted to insert a specific point at a specific place in a data frame, could you?
So the question is, if I really wanted to insert something somewhere, could I? This is a yes. There's usually functions that allow you to do things. So like a nice example of that is that people often want to do something like df.x equals df.y plus df.z. And this is sort of a mutation operation. It's sort of weird to do. But pandas has other methods you can use, like df.assign x equals df.y plus df.z. And so it's sometimes it's just you need to sort of find in the API the right functions to use, the right methods to use. Again, I don't want this to be a Dask tutorial. I want this to be a sort of general computing tutorial, so I'm not talking about these things in depth. But
So what you get back is a gain of distributed data.
yeah, so what you would get back from this is, again, a distributed data frame that has now a longer recipe of how to compute it once it needs to be computed. As we keep adding new operations onto these data frames, that recipe gets longer and longer and longer and longer.
So at this point, since you haven't done compute, X doesn't actually exist.
Correct. Yeah, so it exists logically. We know that it will exist. We know how to produce it. But it's not actually being run and ran at any time. An operation like persist will take that recipe, send it up to the scheduler. The scheduler will compute all of those things and give us back a new data frame with futures in that data frame, actually. And we can call result on those futures whenever we need to. Yeah?
Could you combine the earlier learned things like map and submit with distributed data sets? So if you had multiple tasks that you wanted to do on this big data set, I guess there's no penalty to using what we learned in the earlier part.
Yeah, so the question is, can I combine the previous methods like map and submit with these collections to do maybe some ad hoc computation and then use that to create a data frame and then...
Specifically, the application looking at it is basically doing a whole bunch of plots in parallel instead of doing them sequentially on a distributed data frame.
Yeah, so if you want to do a whole lot of plots in parallel, as you just said, you might make a whole lot of distributed data frames and then compute them all at the same time. So there's the compute method, but there's also like a compute function you can use. And you can give it many different data frames all at the same time, and it'll compute them all simultaneously. But let's talk about that sort of thing. There's lots of fancy things you can do. With Spark, with Dask, with IPython Parallel, there's lots of options. And we could spend many hours talking about the many things we could do. Okay, so you asked a very great question about this last example doesn't fail. So in this example, we are loading out the entire data set, and we're going to compute, so let's load up the entire data set. There we go. And we claimed that df.count.compute would fail. It turns out not to fail. Why is this taking a while? That's taking longer than I expected. 2 minutes? Okay, I probably can't stay up here for 2 minutes. If you do this, you will find that it doesn't fail, but you will find that there are two different columns for rate code ID. And so something you could do if you wanted it to fail is you could do df.rateCodeID.distinct or drop duplicates. This is going to find all the unique values for a rate code ID. And let's actually so what happened here? This failed. Great, we failed early. By connection reset error. Ben, where's Ben? Cluster's dying? Sorry, going back, what you would find is that in our CSV data set, new errors start to occur. There's a whole new family of errors that you can engage in. In this particular case, some of the CSV files capitalize rate code ID, and some of the files do not capitalize rate code ID. And so there's, doable CSV files. You didn't experience this with pandas because there's just one CSV file at a time, but now there's a new kind of error for you, and you'll get new exceptions. And it's interesting to see what happens on how your parallel tools propagate those exceptions back towards you, back to you. Do you get the original exception? Somewhere an error occurred on some machine. We need to sort of bottle up that exception and that traceback and send it back and present it to you. And it's tricky, right? You can't use the Python debugger anymore because it's happening on a different machine. Tools like IPython Parallel are actually really good at this because they can interact with IPython naturally to give you that nice debugging experience remotely. Tools like Spark and Dask don't have those abilities. I apologize, I can't show you that in a more visceral way.
So since we have both you and the IPython guys, what is some trade-offs between Dask and IPython? When would you use IPython parallel and when would you use Dask?
Do you want me to? I'll give my shtick. I would say Dask is better for more complex algorithms. Like these data frame algorithms are actually really complex. If you go to the Dask talk on Thursday morning, you'll see wacky algorithms. And Dask tends to be better at those sorts of things that are more algorithmically complex. IPython parallel tends to be a lot better at imperatively managing a lot of machines. So like you can go to any machine and like type in your IPython session and see what the variables are there, change them around imperatively. You have sort of full control over your cluster. So it's really nice. So actually, IPython parallel is nice in that it'll actually launch a Dask cluster for you. And so you can use both of them, right? You can use IPython to do a lot of your per machine management and tracking what's happening on all the different machines. And you can use Dask to do some of your more complex algorithmics. Is that a fair?
Yeah, I'd say the general difference between IPython parallel and Spark and Dask is that IPython parallel, your remote execution environments are inherently stateful. So you can say like, create a database connection on all my workers and then submit tasks that reuse that object or load data. It's more, you're doing more explicit work assigning individual engines to do particular things. And IPython parallel doesn't have any of the kind of lazy evaluation algorithm stuff that Dask does. So I would say you can use IPython, and that's part of the reason for that is the reason for IPython parallel now has a method to say become distributed, and it just gives you the Dask API to the same resources, so that you can, if you're doing direct manipulation of namespaces, you use IPython parallel, and when you don't want to do load balance algorithm stuff, then you use Dask on the same resources.
I think your S3 connection was reset. Your cluster is fine.
Oh, okay.
But hold on.
It's also worth pointing out that IPython parallel has been around for a lot longer and is a lot more mature. Dask is moving very quickly. There's like fancy things that we do, but it also, has been around less long. There's lots of things that come up in distributed computing that IPython parallel has solved, that Dask will eventually solve after people run into all the rough edges.
It should be faster now than 30 workers.
Oh, let's restart this. I can confirm that. I do indeed have now 30 workers. So let's do. Sure.
You now have 100 workers.
I disagree. There we go. So this is a demonstration that Dask is elastic and can grow. This thing's gone.
So if you add workers while this computation is going on, those will get used?
Yeah, so Dask is elastic and resilient. Workers can die, workers can come back. You have many users can die, users can come back. But whenever I run this thing, things seem to die up here. Yeah, this is not worth debugging at the moment. But, okay, so we've got around 30 minutes left. Let's talk, do you want to talk about the PySpark thing, or should I talk about it? Okay. Okay, so. Okay, so we have one more notebook. Ben is going to talk about PySpark and data movement.
Is there an image there? Where's the... Oh, okay.
Oh, sorry.
Yeah. Okay. Okay. So, so we've looked at some of the data frames. We've also looked at some of the bits of the API that Dask exposes. We also wanted to look at sort of the underlying parts of Spark. So generally, people advise that if you're using Spark, to use the data frame interface. It's very fast. Because it's not really running through Python, all that code sort of gets sort of converted into something that makes a lot more sense in Scala. Because there's this interface, because the data frame executes some known algorithm, you can just re-express what that algorithm should be in another language. Sort of. So to look at this, we're going to go through this canonical count words example, but rather than looking at words, we're going to do a little bit of like gazing at how people use GitHub. So there's a bunch of GitHub data in S3. We're going to grab an RDD of this JSON file, and it looks sort of like this. So GitHub publishes all of its data. It's going to take just a minute to grab 2 of them. And within this data set, you'll see things like the user, the event that they, whether it was a push event, a comment. This is taking longer than I would have expected.
Maybe the dynamic resizing was weird. Try a new cluster. Or just start a new cluster just in case.
Yeah, that's a good idea. I don't know how to.
I would start.
Yeah, I don't know how to use your laptop. Yeah.
It's your button.
I couldn't. Okay. Hopefully I didn't destroy everything. But what we're going to see is basically some examples of, it's really important to understand how these algorithms actually, what they're doing underneath. Spark has this legacy of coming from, actually, how many of you have ever heard of MapReduce or used MapReduce in the past? Okay, so Spark comes from that world of, we're going to take a lot of the concepts that existed in Java MapReduce of things like map, reduce, combiners, aggregators, all the optimizations that people sort of had to learn and had to explicitly understand, like, this is where the data lives. I'm going to try and push all my compute over there and make sure that I don't have to do these very large shuffles. We'll dive into what that means a little bit. So it's PySpark group by. Okay. Hopefully a little faster this time. Oh, great. Ooh, I was a little nervous. Okay. So it's you can see that it's a string, it's a dictionary. It's actually, so if we loaded this in JSON, it will look a little bit nicer. So let's do that. So instead, we're going to take map. We're going to use map and call the function JSON loads on all the things inside of this RDD, but we're only going to take one of them. So this should be relatively fast. So it's the things that you would sort of expect from GitHub, or maybe you don't expect it, maybe you don't know, but here's what you can see. So you can, there's a lot of things in here I don't really care about, but basically we're going to look at the type coming up. That's mostly what we're going to be delving into in this place, but in this example. We're also going to use this JS persist. So persist is similar to Dask's persist, except it will only persist after you've run the computation. So you have to run it first. There's no compute that's happened right now. Sometimes people have there's like a little bit of a mismatch where Dask thinks persist should actually do that computation right away, and so the Spark world thinks, no, you should only persist after you've run this computation. So after we run count, all this data will now be persisted into memory, and now we can continue on with our examples. Otherwise, we'd see some weird timings. So we have around 200,000 elements here. So let's make this a little nicer. So we want to count. We want to count the number of events, or we want to find out how many events happened. We want to find out the groupings of each event. So how many push events happened, how many comments happened. We do this in this very canonical, in this way that we think is actually going to be fairly efficient. There's this group by thing, and we'll call it. Syntax errors. We'll call it. And this is an example of where we're understanding what the underlying algorithm is actually doing. So in this case, this group by is actually doing a very large shuffle. So I'm going to take a break from this and explain what's happening here. So if we wanted to group this room in some sort of way and say like all the columns, every column needs to be grouped together. So everybody in this row and everybody in this row, and everybody in this row needs to all be grouped together. If we say every first row needs to move over to, so everybody in this column needs to move to that table, the next column needs to move to that table, and we keep on going, that's going to be rather expensive because we have to move all of the data to that new row up there. Whereas if we said everybody come together, count the number, everybody here count the number, then we could just move that little bit of number. Does that make sense? I think Matt maybe has a better way of explaining it. Yeah, why don't you? I have a visual aid as well.
So we're going to describe what is called a shuffle and how you avoid shuffles. So if you have a school with a lot of classrooms, and you want to count how many girls and how many boys are in the school, one solution, I apologize for using a gender binary, but one solution is to move all the boys to one side of the school and all the girls to the other side of the school, and then run the length function on both of those groups. Right. That would count everything. But now we have all these kids moving around throughout the school. It gets very confusing very quickly. Another solution is to go to each, so the cluster is the entire school, all of the classrooms, all the different machines. Another solution is to tell each teacher to count up the number of boys and girls in each class, and then send one student to run with that information up to some central place. So there's still some communication, still some students that need to run around, but there's far fewer students. So the group by example Ben is showing is the former case. We're saying, okay, group everyone. All the boys over to the field, all the girls over to the other field. Then count. And this is, you often see people using Spark or Dask in this way, because it's very intuitive to write down group by and then apply length. It's very intuitive to do that. But it's also very, very slow. Now you can also teach all of the teachers how to count things up individually, and then teach other people how to count up those counts differently, how to add those counts. And that's more complex. It's also much, much faster. This is a case where, because you're on a distributed system, communication is now much more expensive than it used to be. You need to change your mental model of what is expensive, what is not expensive. That'll change how you decide to write code. Good?
Yeah. That's great. So we ran this one example with this, as Matt was saying, this fairly inefficient one. So I think that we can do better, but it's going to be a little bit, as Matt also said, it's going to be a little bit more arduous to write. So we're going to take this key by function, which sort of inverts what we have. We want to key off of all the types. So again, push event, issue comment, things like that. And we can now combine all those keys together. So the combine API, let's see. How do I get a cell above? There we go. There we go, okay. Yeah, so the combine API is looking for some lambda that's actually going to combine all these keys together. It's actually not too illuminating. So we have to write. So we're going to do kind of what Matt was just describing. We're going to take all the classrooms, or in this case, all the keys, add one to each element that you have, and then take all those ones together and then add them all together. So we're going to take a group of people, add them over here, and then take those two things and add them together. And now when I run this operation, we get the same result, and it goes significantly faster. So we've gone from 16 seconds to half a second or so. And again, we can also write this operation yet another way. Oh, actually, yeah, with reduce by key as well, which comes off as a little bit of a different form. But here, this is a kind of a better visual aid of what's actually happening here. So this group by actually moves all these things into different groups. You can see that there's lots of network traffic over there. And the reduce by key is actually significantly faster because we're transferring significantly less data. So when we call out to these APIs, if we really need to understand what's actually happening in order to make sure that we're we're getting the speed ups that we think that we should be. Gonna, yeah.
So instead of equivalent in Dask?
Yeah, so Dask looks, you'd have a bag and you say bag.fold by type, and you'd give it a lambda for how to take an element and produce one, and then you give it another lambda for how to combine the girls and boys, the counts. And it would look something like that. So Dask has a slightly different interface that's more influenced by something like IterTools or the PyTools project, where Spark comes more from the sort of MapReduce keying structure. But they both have the same combinational problems. Yeah. The Spark shuffle will be faster. If you use the group by, Spark will be faster. Okay. So there's about 20 minutes left. What I suggest is that we just have sort of free time to play with these data sets on a cluster. I think for a lot of people this is maybe a rare occasion where you have a nice cluster to play with. Can we leave up the cluster for a few hours after this tutorial? Yeah. So you can imagine doing some nice exercises on this data set, like find all the commits that Min made in the last month or in the last year. And it's a nice thing to do. There's lots of them. Yeah. Or find the top committers. You can compare the performance of sort versus top K. This is another example where people often, when they want to find the top 10 elements, they might sort the data set and then just select the top 10. And sorting is actually really hard to do in parallel across the cluster. So there's alternative algorithms like top K, which run a lot faster. Or you can do something totally different. So we'll all be around for the next half hour. Work on whatever you want. And please let us know how we can help you. You guys want to call this the end of tutorial time? Okay. So slides. We run a conclusion before people totally zone out. No conclusion, that's great. There we go. Okay. So we've seen in the first section a bunch of parallel algorithms, things like map and submit and collections. And we've seen briefly sort of how they differ and the sort of different ways of thinking. And we've gotten a little bit of light exposure onto a few different libraries. The goal of this tutorial was not to give you in-depth exposure to any particular library, and I think we've probably succeeded in that. But you can see different kinds of problems, and you can think, okay, here's a nested for loop, here are my options, here's something very weird, here are my options, here's a simple list, I should probably use map. In the latter section, we looked at more complex computational systems like clusters, and some of the issues that arise with those clusters. We sort of got some nitty-gritty experience with that. You can follow us on those GitHub or Twitter handles. And we also want to thank SciPy, the SciPy conference tutorial organizers, our various employers. So Ben and I are both funded by Continuum. Min is funded by Simula and Jupyter. And also Google for the Google Compute Engine credits that we've all been using. So that is it. And we'll be around if you guys have questions.